Alright everybody, today we'll be doing a synthesis using a protecting group. In this problem, we're given compound saying synthesize this, given this molecule, and it seems like normally you could probably just do a simple SN2 reaction using something like NaOCH3, and it would just be a simple attack here. And this would get kicked off and you would get this, but you got to keep in mind, since you have this alcohol present, and instead of it reacting the way you want it to, it's going to instead, the oxygen that is with a negative charge is going to instead attack this and deprotonating this. So instead of getting the result that you want, you will end up with getting something like this. And you don't want this, because now doing this whole thing is going to ruin your whole SN2 reaction. So now, to prevent the acid-base reaction from happening, instead what we can do is use a protecting group, and in this case, to protect this alcohol, we can use something called TBDMS, which is called terbutyl dimethylsilate, which looks something along the lines of this. And what it does is it occupies this alcohol so it can no longer react with this. So in this case, we have this molecule. What would happen is we'd have this alcohol once we have our TBDMS, since the alcohol we have right here, the oxygen is a lot more electronegative than the silicon, so it's going to attack that, which kicks off the chlorine. So what you get from this is, instead of the chlorine being bonded to the silicon, you're going to have the oxygen, and you're going to get something that looks like this. And now we get rid of the hydrogen, which gives us a product of this. And now, since we have done this, before we were worried about the hydrogen being present in an acid-base reaction, since this will end up deprotonating it and ruining the whole nucleophile. Now instead, since the oxygen no longer has a hydrogen attached, instead it's attached to a silicon atom, we no longer have to worry about any deprotonation happening. So what we can do now, since we have this protecting group, is we can actually go on with our reaction with our SN2 and actually use this to get rid of the bromine. So bromine reacts with this OCH3, this is plus minus. This is simply going to do a simple SN2 reaction, which kicks this off, and we are left with this. Now we are two, so now we are left with this, and now all we have to do is get rid of the protecting group and we'll be all done. To get rid of that, we can use something called BU4NF, which then is gonna, the fluorine is gonna end up attacking the silicon, which is gonna end up kicking off the oxygen. So this bond breaks, and instead we are left with something, it's just simple deprotonated alcohol, which gives us this. And now, since all you have left is just reprotonate this, so you could put a solvent in there, they're gonna do the job, which in the long run ends up plus H solvent, which ends up giving you the product you get. That's how you use a synthesis with a protecting group for alcohols. So now in this problem, we're given a synthesis using a carbonyl group instead of the alcohols. We have to synthesize this when we're given this molecule. So now you would say to yourself, oh, that's easy, I'll just reduce this with LiAlH4 and get the product. But instead, the problem with this is, with this reaction, we can't selectively make the reducing agent, which is this, reduce this one specifically instead of that. So what we can do is we can use a protecting group, since we need to protect this. And with that, a protecting group we can use, some of you guys might be familiar with it. You have this diol right here. And the way we do it is we introduce this diol when in acidic conditions, which will cause it to react with this ketone right here. And now you might be thinking, like, why does it react with this ketone instead of this ester? So now the reason why the diol reacts with the ketone instead of the ester is the oxygen that's present right there in the ester makes it receive more electron density, which causes it to be less electrophilic. And since this is more electrophilic, it's gonna more likely to react with the diol. So once the diol reacts with the ketone, you're gonna get something that looks like this. I will have the mechanism for this reaction separately, so you can just pause your screen and look at it if you need to, but for this right now, we're just gonna keep moving on. And once we have this molecule, this is right now protected. So now once we have the diol reacted with the ketone, we get this protected group on it. So now we're free to use a reducing agent and reduce what we need to do with LiAlH4, which gives us a product of this. That's 1, 2, 3. That's 1, 2, 3 OH, and we're simply just left with this protecting group. And just to get rid of this protecting group, all we have to do is react it with something acidic. I'm just going to use H plus, and once again, the mechanism for that is going to be up right now, so you can just pause it and take a look at it. But simply once that's done, is we can, what the hydrogen does, it deprotects, which brings back the ketone that we protected in the beginning, which finally gives us the product. And that's how you do it.